I am in Czech Republic and I am at the Czech Academy of Sciences, UFE. And today what we are doing is to understand the context of the upcoming ASSL conference. And I'm here with Professor Pavel Peterka. Thank you very much for having us. Where are we today?
Welcome here at the Czech Academy of Sciences, Institute of Photonics and Electronics, UFE. We are now at the laboratory of fiber lasers, where we characterize special optical fibers that are then used in fiber lasers development. And I hope that also attendees of ASSL and Optica Laser Congress, or they will have the possibility to come here, and I'm looking forward to meet them here.
Laser manufacturers, nonlinear crystal manufacturers, laser users from all over the world are coming to Czech Republic for this conference. What are the research priorities that you want to share with them?
So at the moment, our research priority is fiber lasers at 2 microns. The people working at 2 microns, they know that there is a barrier of power scaling of these fiber lasers. From 2010, the maximum output power at laboratory devices is about 1 kilowatt. Although the theoretical limits is much higher.
I think that for 15 years we have not increased that power.
Yes, there are some. The main barrier is heat that is generated and in the fiber, so there is problem with cooling. And the cooling of this fiber, it's a big obstacle. How to find the best cooling method?
And how are we gonna solve this?
So I think that we know some keys how to do it. One thing is to proper model the fibers, and for proper modeling we need to know how the spectroscopy parameters change with temperature. And surprisingly, we were the first in this laboratory who measured these spectroscopic parameters in temperatures that are even relevant for high power fiber lasers. It means up to 300 degrees Celsius.
We want to hear about your work on fiber lasers. Bára, what are we looking at?
Yeah, we are looking at the setup of emission spectrum measurement of 2 silica fibers. As was said, the overheating of the fiber is really an issue.
So this is the setup in which you warm the fiber. Is this the hot plate?
Yeah, this is the hot plate, and we have the short fiber piece on it. Mm-hmm. It's several millimeters long, and we heat it up to 300 degrees Celsius, and then the light is delivered backwards to the setup and to the spectrometer.
Bára, as you saw from Pavel, right now this is one of the challenges, having 2 micrometer fiber optics that support higher powers than the one achieved already 15 years ago. Together with Bára, I'm here with Jan. Jan, thank you very much for coming also to this meeting with UFE. What do you do here?
So one of my jobs is to build fiber lasers and characterize the fibers. So we have the setup on the other side if you want to come take a look.
When you talk about fiber lasers, you talk about power and repetition rate and wavelength. What are the 3 parameters for you?
So we mainly focus on continuous wave fiber lasers. So we want to see high efficiency and high continuous wave output power. So here we have some very basic characterization setup where we have a fiber sample which forms the resonator of the laser. We have some pump diodes over here which supply power to the laser, and we can measure the output power of the laser on both sides and measure the unabsorbed output power. At the same time, we can monitor the output spectrum, and all of these parameters allow us to compute the efficiency of the fiber, which is one of the best ways to avoid heat load because you don't generate it in the first place if your fiber has high efficiency.
After understanding the fiber laser business, we want to see the splicing part. I'm here trying to see the new splicing tools that you have. This is your splicing setup, correct?
Yes.
You are working here with many different specialty fibers. You are working with large diameter core. You are working with also hollow core, working with multi-core. How is it different to splice different fibers in this setup?
This setup, one of our key achievement was splicing soft glass Z-bond fiber to silica fiber. These materials are with extremely different thermal properties. We are the first who measured precisely the required temperature window for successful splicing of such different fibers. And it was only 2.5 degrees wide.
So now we are seeing the setup for splicing with a CO2 laser. Can you walk us through it?
Yes, this is the CO2 laser. We place the fiber inside here. These are the different types of holders for the different dimension of fibers. Before placing the fibers in, we cleave the fibers with these cleavers, and we have different dimension holders here as well. So we cleave the fiber, we take it, we place it here, then we close it, then we gonna operate it with the computer, and it splices the fibers.
One of the key applications is splicing hollow core fiber.
Yes.
So what are the main challenges when it comes to splicing hollow core fibers?
As you can see, the hollow core fiber structure looks something like this.
Yes.
So the main problem in splicing hollow core fibers is that if you have too much power in the splice, the whole structure might disintegrate and it might not be in proper shape. In order to avoid that, we use something called cold splicing technique, where the splicing power might be a little lower, or the splicing duration might be a little lower. And the CO2 laser is very useful for this, because the CO2 only interacts with the glass over here and not the air. So we can control how much power is going at the splice point. So we can have a very clean splice without deforming the shape of the hollow core fibers.
Professor Peterka, one thing that I'm noticing is that the community of hollow core fibers is more alive than ever before. A few weeks ago, I went to Limoges, I met Feta, I know very well Professor Buzinski, who is one of your collaborators. You are trying to bring this community together, right, at the Specialty Fiber Conference.
Yes, it was a special occasion. This year in April, we organized the WOSOF, a Workshop of Specialty Optical Fiber Conference, and we had the pleasure it was a great opportunity to listen the plenary paper of Francesco Poletti, and he also told us that the initial design of this revolver, or something similar to this revolver-shaped fiber, was originally developed in Limoges.
Pavel, what makes you excited about hollow core fibers?
Well, we are making these hollow core fibers for short distances. We also doing nested capillary and these theta-shaped fibers, but still the losses are, of course, not that developed. So for short distances is perfect.
Oh, that was really fantastic.
Thank you.
For me, seeing the fiber laser is one thing, but understanding how the fiber is made is another thing. Can we go please see how the fiber is made?
So here we have been in our fiber laser laboratories where we test the fibers, but now we are going to the optical fiber technology lab that is on another part of the building.
I have a plane to catch, let's go. After seeing how fiber lasers are made here in Prague, we came to the place where fiber optics are manufactured. I'm here with Ivan Krasic. Ivan, what are we going to see here?
Okay. Today in our laboratory you will see fiber preparation for fiber lasers, and the fabrication is going in 2 steps. First, the preform is prepared. It's a material that deals with material research. It must be anchored some material properties inside the fiber.
So this is the preform, made of fused silica.
In the second step, the fiber is drawn from the preform in the same structure.
So we're going to see here how fibers are made from the preforms all the way to the drawing of the fiber and how the fiber is qualified.
Yeah.
Ivan, this is one of the most beautiful setups I've seen in my life. What are we looking at?
We are looking at the glass lathe for fabrication of preforms. It means that it's turned with low rotation, and it's possible, instead of any tool, there is a burner, and by this burner we heat the glass to deposit some layers and finally to collapse it. In this step, the temperature will be increased to high temperature.
What is high?
High means around 2000 degrees centigrade.
Wow.
You can have a look. And thanks to slow rotation, thanks to slow speed, we will try to collapse the tube, the deposited tube. You will see that something is inside, and we will collapse it to the rod. You can see that the process is really slow, and now I will stop the process, and you can see that really the tube is of smaller diameter, still some hole stays inside, and in second or third step you will be able to collapse it. Nowadays it's like nicely visible, and thanks to some dopants, some change of material composition, you can see the reddish coloration inside.
Ivan, this looks like craft. This looks like art to me. To what level can you control the dimensions?
Difficult. The technology parameters are flow rates of the standing materials inside material composition. Second, must be perfectly controlled temperature by pyrometer. And finally, the wall thickness of the substrate tube must be perfect. And talking about tolerances, the maximum tolerance is 2%. So when the wall thickness, original wall thickness is 2 millimeters, so 1% is 0.2 millimeters, and all the tolerances must be within 2%. That is not easy.
Ivan, I think once we have seen the art of making a preform, can we see how the fiber is drawn?
Yes, this is like art. It is when the preform is not successful, then we obtain the nice arts for Christmas trees, but unfortunately expensive.
Let's go to see the tower. So after seeing the preform, we came to the top of the tower. Where are we right now, Ondřej Podrazký?
We are at the top of the drawing tower, and we are going to put the preform into a furnace and start the beginning.
What am I looking at right now?
It's a silica preform, so we will have to heat the furnace up to 2000 degrees C to make it soft enough to be able to draw the fiber.
Okay, so let's start.
Let's start. So it will take some time.
So now the preform is going down.
Yeah, my colleague is pushing the preform down. And once the preform is in position, we will have to heat up the furnace.
Okay, and you heat up the furnace to 2000 degrees centigrade.
Approximately 2000.
How important is to keep the temperature accurate to the degrees centigrade?
It's very important since maintaining the fiber geometry is crucial for parameters of the resulting fiber.
So the fiber coming from the third floor, we are now at the second floor. The fiber was drawn to here. What is happening on this floor?
And in the middle of the drawing tower, we have a coating die, which coats the bare fiber with acrylate polymer in this device. And some 1 meter lower, there's a strong mercury lamp which cures the fiber during few seconds. Or the polymer standard coating for
so the fiber is drawn through here, through the UV curing station, all the way down.
Yes.
Shall we go down?
And yes, and everything has to be centered precisely, so we have a good concentricity of the coating to the fiber. Yes, and the fiber is now coated, so it's strong. You can test by yourself that it's really, you can't break it. Yeah.
The magic done live. Thank you so much, Ondřej, for this.
You're welcome.
You all witnessed the manufacturing of fiber optics here.
Yeah. And if you stay another hour, we will draw 1 kilometer of fiber.
Doping with germanium and phosphorus is critical. Can you walk us through the process in the setup for the doping of the fiber?
The process must be carefully controlled, and for example, for erbium or ytterbium doped fibers, it's important the level of doping of phosphorus pentoxide.
We're talking about rare earth materials. How difficult it is to get those materials here in Europe?
Yeah, difficult. And that's why it's necessary to apply completely another technology. And we developed our original nanoparticle doping technology, and we used nanoparticles for incorporating them into substrate tube. It's completely different approach.
Using those nanoparticles is a solution, but
Yes.
Can we actually recycle this rare earth material?
Yes. We are in contact with colleagues responsible for recycling of rare earths, but this is not to recycle our products because there is already several ppms of rare earths inside. But better is to recycle rare earths from, for example, segways and so on, the engines, where the content is roughly 30%. And we try to be independent in Europe from other countries and to recycle our materials as a starting materials for our process.
Professor Peterka, we have been seeing one of the most amazing tours I have seen since I work for Optica. What support are you getting from international funding, such as the European Commission or others?
Yes, currently maybe our most important projects are co-funded by European Union. One of them is Project LASAP, we already talked in the fiber laser labs. And another one is Project TALOS, Tactical Advanced Laser Optical System, that is funded by European Defense Fund. Mm-hmm. And there we are developing tulip fibers for high power stage of the laser.
Before I go to catch my flight, what message do you have for the ISSL conference attendees?
So first of all, don't miss this opportunity to come to ISSL Laser Optical Congress, and when you be here, so think about coming to us and visit our laboratory. And if you have some special idea, we are open for collaboration.
See you at ISSL and at the lab tour here at UFE.